Hi everyone and welcome back to my channel. So today we'll start with the part 3 of our pipelining topic, instruction pipelining. So we have already learned about hazards. We have learned about control hazards in the starting of the introduction of the hazards. Then we learned about data hazards. So today we'll dive more deeper into the control hazards and also the structural hazards. So today we'll learn about two hazards. Mainly there are three types of hazards. So we learned about these two, and then we'll do questions on hazards, all the questions. Okay, so let's start with control hazards. What are they I've already explained those previously in the starting of the hazards topic. What is it? Let me give you an analogy. Okay, so a driver is unsure whether to turn left or right at an intersection because the direction depends on the sign further down the road. Okay, what does it mean? Where I have to turn, you can take the help of Google Maps. Okay, G Maps. You turn on your Google Maps. Okay, and then you put the location of your home. So whether you need to turn to left of the road or to the right of the road, in which direction you need to turn, once you reach this point, right, then only you will be able to see, because you let's assume that you are not able to observe the traffic. Only you are able to observe the traffic once you reach at that particular point. So from this point you are able to observe that the left turn has less traffic, so obviously you will take the right turn. Okay, so you have to wait for some condition to happen, then you decide at that point only that which turn you need to take. So this is like control hazard, because I cannot instantaneously, I am 5 kilometers before and tell that I will take the right turn. I cannot say that. I have to wait which turn I need to take. So that is what a control hazard is. Basically, the driver has to wait for the sign to make a decision. He has to wait for the traffic to make a decision, delaying the movement. In pipelines, a branch instruction causes the pipeline to wait until the branch condition is evaluated, generally in the execution phase or sometimes in the write back phase. It will be given in the question. Okay, so until the outcome of the pipeline of that this current instruction is clear, I will not be able to execute my next instructions, because I don't know if the next instruction is supposed to be executed or not, because I may have to take some other target instruction, that is some other place. Okay, I7, I6, not I4. After I1, I2, I3, I may not need to fetch the instruction I4. I directly may need to go to I7 or something. Okay, so that is what your control hazard is. So it occurs when the pipeline encounters a branch instruction and must wait to resolve the branch, right? If this is, let's say this is a branch instruction, if I don't wait for the branch instruction to get resolved, what will be the problem? The problem will be that if I start my instruction fetch here and the condition of branch evaluates here, and after evaluating it is telling me target instruction, I have to take the branch, so I have to go to instruction 6. So I was not supposed to fetch instruction I4. After this instruction I3, I was supposed to fetch instruction I6. So that's why I have to wait for these two instructions. I don't do anything in this, in this whole operation, right? From this I will not fetch here, I will not fetch here as well. All this will be no operation. Basically all these cycles will be simply no operation. Okay, so only after this execution phase, right, finally the branch has been evaluated condition. So I will send a signal to the pipeline or something. Okay, so it will understand what is the next instruction to be fetched. So now I will fetch the next instruction. If the branch is taken, I will fetch I6. If the branch is not taken, so this will be fetched when branch is taken. And if branch is not taken, right, simply I4 will be executed, fetched. Branch is not taken. Okay, so that is the case over here that you have to understand. So next is what exactly is happening. That is, they have explained that pipeline stalls cycle 6. So this cycle, right, cycle, okay, 6 and okay 7 will not be stalled. Actually pipeline stalls during cycle 6 and 7. It not stalls during cycle 6 and 7, it actually stalls during cycle 4, 5 and 6 actually. Okay, instruction begins, yeah, 6 and 7. Why is it it should begin fetching at 7 and okay, pipeline stalls during cycles 4, 5 and 6 to resolve the branch. Once resolved, the instruction 6 begins fetching. Thus, in the cycle 7. If the branch is resolved, if the branch is second, then obviously I will go to the target instruction. The target instruction, not instruction 6. The target instruction will be fetched. It can be 4 or 6 depending on the result of the branch. Okay, begins fetching in the cycle 7. So we fetch the instruction, target instruction, in the cycle 7 after these many stall cycles, right? We have to give this many stall cycles. So that is what is it telling. The pipeline is stalled and all stages after the branch instruction are emptied. Basically here, right? If let's say we would have done some instruction fetch here, we would have emptied it. We would have not done anything. We would have and then cancelled it. Basically deleted it. Okay, so that is known as pipeline flushing. If I would have simply done like you told me that don't wait. I will do my instruction fetch here. I will do my decode instruction here. I will do my operand fetch. I will again do my instruction fetch here in this instruction cycle 5, and I will do my decode instruction here. I will not wait. But actually, let's say I would have done all this, right? Then finally, after this execution, evaluation of the branch condition, I got to know that I have to actually go to instruction 6. Then whatever I have done, right, all those things I have to delete because those are of no use. Because actually those I shouldn't have taken the branch. I should not have not taken the branch. So I would have to delete all this. Okay. So deletion is also known as flushing. Deletion. Of flushing. Okay, so that is what it is telling me. It is known as pipelines are emptied or delete, or also known as pipeline flushing. A general pipeline cannot inherently solve control hazards, requiring software or hardware based solutions that I have discussed in the starting of the hazards chapter, right? So how do we implement software solutions? The compiler provides the stalls or no operation. Okay, so like here, like same thing is written. If the branch condition is resolved during the ith stage of the instruction cycle, the number of stalls introduced by the branch instruction is given by I minus 1. That I have already derived in the starting of hazard, right? I have already explained why is this happening. Now, when will the branch condition be resolved? Will be given ith stage. This thing, right? When will the branch condition be resolved? Will be given in question. If nothing is mentioned, assume execution phase. Okay, you have to assume execution phase. The number of stalls, okay, this has already been done. This represents the number of pipeline stages that must wait until the branch decision is finalized, delaying the fetching and execution of the subsequent instruction. So here, right, how many stall cycles I needed to provide? My execution was happening, my evaluation of the branch condition was happening in the 1, 2, 3, fourth stage. So how many stall cycles I need to provide? 3. 4 minus 1, 3. So exactly that is what I have told, right? 1, 2, 3. 3 stall cycles. Then again, after that, my next instruction gets fetched. So that is what I'm doing. So in this example, in our current example, I had to give my branch condition was getting evaluated in the 4th phase. So stall cycles and stalls will be 4 minus 1, that is 3. Okay, it is 3. So that is the case over there. Let's do few questions from this. We will understand this is a GATE 2000 question, which is a very, very lengthy question. An instruction pipeline has 5 stages. So K is equals to 5. I will write here K equals to 5, where each stage takes 2 nanoseconds and all instruction use all 5 stages. So like TP is basically 2 nanoseconds and all instructions use all 5 stages. So all instructions always use all 5 stages. What are they saying? Branch instructions are not overlapped. That is, the instruction after the branch is not fetched till the branch instruction is completed. So we have to complete the branch instruction, then only the next instruction will be fetched. Okay, here what does it mean? Branch instructions are not overlapped. That means they have provided as the explanation until the branch instruction is not fetched. I will not fetch. Is not evaluated or completed. Is not executed. I will not fetch the next instruction. Sorry, like I don't have space, that's why I had to write it like this. Okay, so that is the meaning of this. That is the meaning of the branch instruction are not overlap. Let's read the question further. Calculate the average instruction execution time assuming 20% of all the instructions executed are branch instructions. Ignore the fact that some branch instruction may be conditional. So we'll just ignore some branch may be conditional. We'll ignore the fact. What we know is number of branch instruction, right? NB. If I have total n, if I have total n number of instructions, then out of this n not branch will be simply 80% of total number of instructions, and n branch will be total 20%. 20% of instructions are branch type instructions. They are asking me to find the average execution time. Average execution time assuming the 20% of all instructions are branch type instructions. Okay, so let's first solve the first one. Okay, so when does the branch condition gets evaluated? So here they have told me branch condition will be evaluated after the instruction gets completed. So at what stage? If I have for the option A, I have total 5 stages, right? S1, S2, S3, S4 and S5, and they're telling me only after the branch instruction is completed, then only I can start the next instruction fetch. So obviously stage 5 will be the time at which branch instruction is completed. So how many stall cycles and stalls I need to provide for every branch instructions? And stall will be what? It will be, this is the first, second, fifth phase, right? So 5 minus 1, 4 cycles. For 4 stall cycles for each branch instructions. Okay, so I will not write install. Install will be the total number of stalls that I need to provide for how many. So installs will be what? Total number of stalls that I need to provide for how many? For 20%, that is 0.2 n instructions. If one branch instruction causes 4 stall cycles, how many 100 branch instruction will cause? 400 stall cycles. If one branch instruction causes 4 stall cycles, how many will cause? Then 0.2 n branch instruction will cause how many stall cycles? 0.2 n into 4. So n stall will be 0.2 n into 4. Okay, so it will be 0.8 n. And what are they telling me? Average execution time. Okay, so basically they are asking me average execution time, that is CPI. They are asking me, so not CPI, actually average execution time. So what is average execution time? of a single instruction. Like here they should have mentioned average execution time of a single instruction. So T execution average, right, will be what? It will be total execution time, that is T execution, total execution time, okay, of the pipeline system, then divide by the number of instructions, because I have to find out average. On average, how many each instruction take how much time? On average, each instruction take how much time? Simple arithmetic mean, divide by n. Okay, let's just take 100. I have 100 instructions. So if I have 100 instructions, out of those 100 instructions, 20 instructions will be branch time instructions. Okay, so and those 20 branch time instructions will cause how many hazards? How many stall cycles? They will cause 0.8 into n. That is 80 stall cycles. So what I need to find out of 100, on an average, each instruction will take how much time? Okay, so that I need to find out. So T execution pipeline will be total number of cycles. What is the total number of cycles? It will be K plus N minus 1 plus N stall. The extra stall cycles that I needed to provide due to this happened due to what? Due to control hazard. Control hazard. Into obviously TP divided by the total number of instructions, that is N. That is my average, T execution average of a single instruction. Okay, so this will be K is simple 5, N is simple 100, not 100, like N is N only. Okay, N is N only, because they have not provided me how many instructions actually I am fetching, right? They have not provided me the value of N. Okay, so I will assume N to be very, very high. That is my assumption basically. So plus N minus 1 plus N stalls. N stalls will be how much? Now you cannot simply replace this N with a number, right? So I'll show you one example. Let's do an example, that is assume N to be 100. Okay, let's first do example. Assume N to be 100. Then you will understand this better. If N is 100, so my branch instruction will be 20. So my number of stalls, total stalls will be how much? 20 into 4. Each branch instruction takes 4 cycles. So it will be 80 stalls, right? So now what will be my average execution time? Average execution time will be what? This will be like I have 5 stages plus 100 instructions minus 1 plus number of stall cycles, 80 stall cycles I have, into 2 nanoseconds, right? This is 2 nano, remember this is in nanoseconds. Okay, divide by the 100. So this will come out to be, I will calculate this. This will come out to be 105 minus 1 plus 80 divided by 100 into 2 is also there. So 3.68 nanoseconds. So if I have 100 instructions, then each instruction on an average will cause 3.68 nanoseconds. But actually this is not the correct answer. Okay, I will explain why. So now we won't be able to assume any N because they have not given N. So my assumption will be N is very, very greater than K. That is my assumption. K minus 1. Okay, so what was the formula? Formula was this, right? Formula was this. So my T execution average, my K is 5, that is fixed, plus N minus 1. How much is N stall? It is 0.8 N, right? I have already computed it. It is 0.8 N into 2 nanoseconds divided by N. Now my assumption is that N is very, very large. If N is very, very large, right, overall what will this become? This will become 1.8 N minus 4 into 2 divided by N. So if N is very, very high, just assume N to be 1000, N to be 10,000. So this minus 4 I can ignore. So this will become 1.8 N divided by N into 2. So this will become 3.6 nanoseconds. Okay, if n is very large, right? So execution time will actually reduce. Average execution time will actually reduce. It will be 3.6, not 3.68. I just assume n to be 100. Okay, but this is how you solve, right? You use the concept of limits. I hope you understand the concept of limits. So this is the part A. Okay, this is a very good question, and this is the part A basically. Let's solve the part B. What is the part B telling us? So in part B, if a branch condition is a conditional branch, so it's a conditional branch. Okay, now they are telling me if it's a conditional branch instruction, the branch need not be taken. So if it is a conditional branch, it may happen that we don't take the branch. It depends, right, on the evaluation of the condition. If the condition is true, we take the branch. If the condition is false, we don't take the branch. So that is what they're telling. We already know this. So what it means is, if the condition is true, branch taken. If it is false, branch not taken. Okay, the following instructions can be overlapped. If the branch is not taken, the following instructions can be overlapped, right? If the branch, let's say if the branch is not taken, right, the instruction can be overlapped because I don't have to wait. Okay, so when 80% of all branch instructions are conditional instructions and 50% of the conditional branch instructions are such that the branch is taken, calculate the average execution time. So this is a tongue twister and bit difficult to understand. So actually, what is unconditional branch? Unconditional branch means I have to take the branch anyhow. If it is unconditional, then the condition is always true. Like, I will always follow the condition, right? So I will write here, if the branch is unconditional, I will take the branch always. I will always take the branch. So that means I have to wait, right, until the current instruction get executed, because if I am branching, then I have to wait, because they have told me, right, if I am branching, obviously current instruction needs to be executed first, then I will go to the target instruction. I cannot simply do sequential operation. I cannot do sequential operation. Need to wait for the current instruction. Okay, current instruction. So I will need to wait for the current instruction. So I have to actually wait if it is a unconditional branch. So point 1, if it is unconditional branch, I will wait. Now point 2, they have told me that out of 80%, when 80% of all branch instructions are conditional, so overall branch instruction I have NB, out of that 80% are conditional, 20% are unconditional. Okay, point 1. Then 50% of the conditional branch instructions are such that the branch is taken. So 50 out of those, 50% are such that branch will be taken. So simple thing is, whenever branch will be taken, stall cycles will be introduced. So second point is, whenever branch is taken, stall cycles will be introduced. Okay, if branch is not taken, right, if branch is not taken, then no stall cycles. Why no stall cycles? Why is that? Because I am doing sequential operation. Because after I3, I4 was supposed to come and it is coming. Branch is not taken, right? I am not going to I7. Sequential operation. Okay. So that is what happened. That is a point. These are the two important points that I need to understand. So let's first draw the T diagram. So if I have n instructions, out of those n instructions, this information is already given. Okay. Out of those n instructions, right? In the first part, they have already told me that I have 20% are branch instruction. So, okay, 20% are branch instruction, that is already given in the part 1, right? So 20% are branch instructions. So here n not branch is 0.8 n and n branch is 0.2 n. I have 20% branch instruction. Now out of this, right, out of this 20% branch instruction, they are telling me something. What are they telling me? They're telling me that out of this 20% branch instruction, right, when 80% of all the branch instructions are conditional branch instruction. So 80% are conditional branch instruction. Out of all the branch instructions, 80% are conditional branch instruction. So I will do 80% of this. So what is 80% of this? I will simply multiply 0.8. So n conditional branch instruction will be simply 80% of this, right? So 0.8 into 0.2n. Okay. Also, remaining will be unconditional branch instructions. Unconditional branch instruction. What will be the remaining? Simply 0.2. You can either do 0.2 into this number, or you can simply subtract from this number as well. This number, you will get back the same result. Okay, so overall this is what? This is basically 0.16n and this will be 0.04n. Okay, and next what they're telling me? They're telling me out of this conditional branch, right? Out of this conditional branch instruction, 50% of the conditional branch instructions are such that branch is taken. So I already know the result. So 80% are conditional branch instruction, and out of this 50%, so conditional branch taken, it will be, I have to multiply 0.5, right? 0.5 into 0.16n. And conditional branch not taken, it will be 0.5 into 0.68 only, 116 only, it will be 0.08n. Okay, so this is the basic tree diagram, right? This is the basic tree diagram. I hope you have understood this thing. So this is the actual happening, right? This is the actual thing. So calculate the average instruction execution time. So how do I find out the things here? So one thing I have to understand is that I have told you a point. Whenever the branch is taken, I will introduce stall cycles. If branch is not taken, I will not introduce any stall cycles. So how many total number of branch instructions where branch is taken. So it will be simply, I can give a notation, branch T, branch is taken. So it will be simply equals to, if I come back here, right, this many instructions, conditional branch instructions I have, where I know condition will be true and branch will be taken. Also, I have unconditional branch instructions. So those will be taken regardless. They don't have any condition associated with it. So those branch instructions will be taken. I don't care about those. So this plus this. Okay. So it will be NCBT plus N unconditional branch instructions. So how many NCBT I have? 0.08 N, basically both are same only. 0.08 N plus unconditional is 0.04, I think. Yeah, 0.04 N. (0.04 N). So what will be the total stall cycles introduced? The total stall cycles, right? N stalls. N stalls will be simply how many total branch I will take? 0.12, right? And for each of this taken branch, I have to introduce 4 stall cycles. That is 5 minus 1, 4 stall cycles. So it will become 0.48 N. So now finally, I can write the average execution time for the part B. So this is right. This is for the part B actually. We will write from here. So this will be equals to K plus N minus 1 plus N stalls into TP divided by the total number of instructions, that is N. We started with N, right? So again, I can ignore K minus 1 as N. I will assume my N to be very larger. N to be very larger than K minus 1. So obviously I can ignore this. So this will be equals to 1.48 N into 2 nanoseconds divided by N. So it will be 2 into 1.48. So it will be almost equals to 2.96. Okay, this is C won't work. 1.4, just hold on. It is 2.96, I know that. Just I want to calculate. 1.48 into 2, yeah, 2.96. So average execution time is 2.96. Now you can see that if branch is like few branches were not taken, right? Previously what I was doing, I was actually giving time for all branch instructions. So now some way I got to know that few branch instructions are taken and few are not taken. So I can actually not give stall cycles where branch instruction is not taken. So I can save time. So this is how our current processors save the time, save the execution time. You can see the average execution time has reduced. It was previously 3.6. Now it has reduced to 2.96, right? Almost 0.6 nanoseconds has been reduced. So this is how we do branch prediction. Previous lecture I told you we use some branch prediction techniques. So this is how we save the time, execution time, by predicting the branch. Okay, so that is for some other topic. We will not go into that. Okay, so I hope you have understood the concept here. Okay, so let's solve the next question of this particular similar type of topic only. So this is again like whenever hazard question comes, right, it's a very big question and student gets scared by just seeing the length of the question. Okay, by just seeing the length of the question they get scared. So an instruction pipeline has 5 stages. So I have 5 stages. First is instruction fetch. I will write things. Instruction fetch, instruction decode, and register fetch. So operand register fetch happens here simultaneously. Okay, happens here simultaneously. And then I have instruction execution, EX. Then I have memory access, MEM. So they will mention what each thing does. Whatever is required, they will mention it. And then I have register write back. So WB. Okay. Each stage with latency is 1 nanosecond, 2.2, 2 nanoseconds, 0.75. So from here, can you find out the TP? TP will be what? TP will be maximum of 1 comma 2.2 comma 2 comma 1 comma 0.75. okay, nanoseconds. So this will be equals to how much? This will be simply max of 1, 2.2 to 1.7. So TP will be 2.2 nanoseconds. Okay, and what else? What else they're telling me? To gain in terms of frequency, the designers have decided to split the ID/RF stage into 3 stages: ID, RF1, RF2. So this ID/RF phase, right, has been split up into 3 phases: ID, RF1, RF2, each with latency 2.2 by 3. So now this highest latency, right, of a stage has been reduced to 2.2 by 3. So now can you tell me what will be the pipeline time? This is TP1 actually. What will be the TP2? Now I will have 5 stages. K will be equals to 5, not 5, sorry. Previously I had K was equals to 5 only. Now K will be extra 2 stages has been added. ID, RF1, RF2. RF1, RF2 is extra. So it will be total 7 stages. And TP, it will be maximum of 1 divided by 2.2 by 3. What is 2.2 by 3? 2.2 by 3 is 0.73. 0.73. Okay, then everything else is same. 2, 1, 0.75 nanoseconds. Okay, so TP2 is maximum of this. So what is the maximum of this? Maximum of this will be, now maximum TP has reduced. It will be 2. It will not be 2.2 anymore. 2.2 anymore. It will be 2 nanoseconds. Now also the execution stage is split into, okay, also the execution stage is also, I should have written the read the question. Execution stage is also split into 2 stages, that is execution 1 and 2, each of latency 1 nanoseconds. Oh, so sorry, so this K also, this will become now 8 actually, because this, right, this is the execution stage, right, where it was previously taking 2 nanoseconds. Now it will only take 1 nanoseconds each. So I'm sorry, so this also has been splitted up into 2. 1, 1. So my TP will be 1 nanoseconds. Okay, because highest is 1 nanoseconds only. So I have reduced my TP cycle time, but the number of cycles has increased. Now what they are telling me? The new design has a total of 8 pipeline stages, as I have written here, 8 pipeline stages. A program has 20% branch instructions. So as I read the question, I will just draw the tree diagram. That will be very, very helpful to me. So a program has 20% branch instructions. Okay, so n branch is 0.2n and n not branch is 0.8n. okay, next, which execute in execution stage. A program has 20% branch instruction which execute, like it, what is telling, which execute in the execution stage and produce the next instruction pointer at the end of the execution stage in the old design. So what is this telling me? This is telling me when does the branch condition gets evaluated. So I told you, right, they will give you in the question when does the branch condition gets evaluated. So the branch condition for this type 1 of system, branch condition gets evaluated. For type 1, it gets evaluated after execution stage, and for the type 2 system, they would tell me it gets evaluated after the execution 2 stage, at the end of the execution 2 stage. Okay, fine. If the instruction fetch stage stalls after fetching a branch instruction until the next instruction pointer is generated. So until the branch condition gets evaluated, then only the next instruction fetch will occur. It will start. Okay, restart. So all instructions other than branch instructions have an average CPI of 1. In both the designs, all the instructions other than branch instruction has an average CPI of 1. What does average CPI of 1 means? I will explain. Just hold on. Average CPI average is 1 for non-branch instructions. What does it mean? What was the meaning of CPI? Meaning of CPI was cycles per instruction. So if I have n instructions, n number of non-branch instructions, each n number of non-branch instruction will take n cycles. So if I have NB, like this non-branch instruction, they will take NB amount of cycles, right? And what is NB? Not NB equals to 0.8n. So I will take 0.8n cycles to evaluate. Okay, all other instructions has this many cycles, so it will take them 0.8n cycles to evaluate that particular instruction, non-branch instructions. The execution times of this program on the old and the new design are P and Q nanoseconds. So they are not talking about the average execution time, they are talking about execution time. So in system 1, the execution time will be Tx1 and it will be Tx2. And what are they asking? They are just asking me, this will be Tx2. They are just asking me what? They are asking me the ratio of Tx1 over Tx2. Tx1 over Tx2. So they are asking me this, right? They are asking me the ratio of Tx1 over Tx2. So for this, I need to find out the Tx1 and Tx2. Okay. So how do I find out? So first I will write for system 1 P, okay, and Q, system 2. I will do side by side. So actually, how many stall cycles I need to provide? N stalls for system P, right? For system P, number of branch instructions is constant, right? 0.2n. And if they have told me I have to wait until the branch only, then only I will be able to start my next instruction fetch. Correct. So I have 0.2n number of branch instructions, and for each of these branch instructions, how many cycles I have to wait? Here comes the interesting part. How many cycles I have to wait? I have told you, if the branch instruction is evaluated in the ith phase, the number of stall cycles that I need to provide for a single branch instruction will be I minus 1. So it is getting evaluated in this phase, right? In the branch instruction is getting evaluated in the execution phase. And what is the execution phase? It is the 1 to 3rd phase. 3rd phase, right? So here it is the 3rd phase. And in execution 2, it is the what phase? It is basically in execution 2. If I just, okay, I haven't written it down, so I will write it down. Okay. So this is for P and this is for Q. I will write down the stages actually. So first I have instruction fetch, then this IDRF has been divided into IDRF to RF1, then this execution, then execution also has been divided into 2 stages, execution 1, execution 2, then memory, then write back. So here, right, here my branch conditions gets evaluated in the second type of system. So what stage is this? 1, 2, 3, 4, 5, 6. In the 6th phase, right? In the 6th phase, my branch condition gets evaluated. So here, right, for one branch instruction, I have to provide 3 stall cycles. For 0.2n branch instruction, I have to provide, 2 stall cycles. So it will be 0.2n into 3 minus 1, that is 2 into 0.2. In Q system, for one branch instruction, I have to provide 6 minus 1, 5 stall cycles. Okay, but for 0.2n branch instruction, I have to provide 0.2n into 6 minus 1. So this will be 0.2n into 6 minus 1. Why am I writing 6 minus 1? To show you the significance. Okay, to understand the significance that this 6, right, is the phase where the branch instruction gets evaluated. So this, like, I am stressing on this point because I know there will be doubt. So this is the phase where the branch instruction gets okay. So this will be how many stalls? This will be 0.4 n stalls, and this will be 1, like basically n stalls. Okay, now I need to find out the execution time. So how do I find out t execution time of p or 1? See this, right? I can write this as p as well, p over q, right? That is what they're asking me. So execution time of p will simply be equals to, if I didn't have any hazard, how many cycles I required. So how many remaining cycles are there? So if I didn't have any hazard, right, normally how many like cycles I needed to provide? Normally how many cycles I needed to provide? K plus n minus 1, correct? K plus n minus 1. This is the number of cycles that I needed to provide. This is Kp actually. This will be Kp. Plus the extra stall cycles. This is n stall p. This is n stall q. N stall p. Okay, this will be equals to how much? This will be, as n is very large, so we can ignore the k. N is very large. My assumption is n is very large, so it will be 1.4 n into, obviously you forgot the tp, right? You have to write the tp of p. Okay, so it will be tp of p is 2 nanoseconds, so it will be 2.8 n nanoseconds. Now in this case everything will be similar only, but values will change obviously. So it will become TPQ, this will be Q, this will be Q, and this, right, will be n plus how many stall cycles? N stall cycles, right? So this will be 2n actually, n plus n into 2 into what is the TPQ actually? What is the TPQ? TPQ, right now has become here, if you see, it is 1 nanoseconds only. So it is 1 nanoseconds only. So it will be 2n nanoseconds. And what are they asking? They are asking me the ratio of t execution p over t execution q. So obviously there has been some improvement, right? So it is 2.8 n divided by 2n, so it is 1.4. so this is, by this much approximately I have improved. Sorry, was this 2 nanoseconds or 2.2? just hold on, this was actually 2.2. sorry, this is 2.2, right? So this will simply not be 2 nanoseconds, this will be 2.2 actually. It will be almost 3.08. so this will be 3.08 n. So obviously things will change a bit. This will become 3.08, then this becomes 1.54. okay, so the ratio becomes 1.54. so this will be the answer of the question. This is also, actually, if you don't know, indirectly they have asked the speed up, basically. Speed up between what? Speed up between system 1 and system 2. This is not comparing with non-pipeline, this is comparing with system 1 and system 2. That's it. Okay, so that is what we are comparing. For this pipeline, answer will be 1.54. I hope you have understood this. Now I know many teachers, I have seen many educators just use the formula. CPI is given, right? They will use some formula and you will not be able to understand this. Okay, so I have tried to keep things as less formula intensive as possible, as conceptual as possible. Okay, so I have not written any formula anywhere, right? I have directly solved with concepts. Okay, directly I have written the concepts here. This is a formula, yes, but I have explained what does each term mean here. So obviously my assumption here is n is very greater than k. That is my assumption. Okay, so that is the first thing that you need to understand and that you need to identify. Okay, this, for some reason this gets opened. Fine. Okay, so yeah, I hope you understood this thing, that for n instructions, how many cycles I anyways would have required? N cycles, but extra cycles I have to provide with install due to the extra branch instructions. Those branch instructions are also instruction only. So normally, if I didn't have to evaluate the branch condition, I would have taken n cycles, but I had to provide few extra stall cycles because few of them were branch instruction. And how much extra stall cycles I needed to provide? This number of branch instructions multiplied by the extra number of cycles per branch instruction. This is the extra amount of cycles that I needed to provide in addition with n instructions. Okay, so here CPI equals to 1 signifies what actually? If you want to understand what does CPI equals to 1 signify, CPI equals to 1 signifies that indirectly they have told you that n is very greater than k minus 1. Why? Because what is CPI? CPI is cycles per instructions, and in pipeline I know new execution of new instruction takes only single cycle when n is very large, right? If n is very large, at every cycle I am getting a new output. It is a pipe and pipe is fully filled, so at every cycle I am getting a new output. So that indirectly they are telling you that n is very larger than k minus 1. Okay, so this question is very elegant and very good question and lengthy question as well. So I know students get scared from this question, and trust me, even the CS branch student won't be able to solve it using basic concept which I have taught you. Okay, you are EC, but you will be able to solve better than those guys. Okay, trust me, you know COA better than those CS branch guys. Okay, so yeah, let's study the next question. So in the next question, a CPU has 5-stage pipeline and runs at 1 GHz frequency. So CPU has k equals to 5 and the frequency, clock frequency, is 1 GHz. Instruction fetch happens in the first stage of the pipeline. Instruction fetch happens in the first stage of the pipeline. A conditional branch instruction computes the target instruction and evaluates the condition in the third stage. So here my I is equals to 3, right? At third stage, I am evaluating the condition of the branch. Okay, so this is very important thing. The processor stops fetching new instructions following a conditional branch until the branch outcome is known. So obviously the same thing only, we'll stop our instruction fetch if I currently am executing a branch instruction, and then I will execute the branch instruction. I will execute the next instruction after the evaluation of the condition of the branch instruction. So I have to wait till this third phase, right? So a program executes 10 raised to power 9 instructions. So my n, I will assume n equals to 10 raised to power 9. Out of which 20% are conditional branches. So again I will draw the tree diagram. So n is here, and out of this n, 0.8 are actually non-branch instructions, and this is 0.8 in, and 20% are branch instructions. Actually 20% are branch instructions. Okay, so next what they are telling me, if each instruction takes 1 cycle to complete on an average. So basically they have given me CPI average each instruction that it is taking one cycle to complete. I already know this. In pipeline, each new instruction take only one cycle to complete, because it is pipeline, right? Pipeline is already filled, n is very, very higher than 1. I already know this. Even though they are telling me, I already know this. The total execution time of the program will be, what will be the total execution time? So they have given me f clock, right? From this, I will be able to find out my cycle time, TP. TP will be 1 by f clock, or this will be 1 nanoseconds. Okay. So I know how many stalls I needed to provide. I have branch instructions. 0.2n are branch instructions, right? And I know each branch instruction will cause how many stall cycles. It will be I minus 1. So 2 stall cycles, 2 extra stall cycles I have to provide for each branch instruction. So it will be again 0.4 n. Okay. And overall, how many number of, like, what will be the total execution time of the pipeline system? It will be simply total number of cycles, which is k plus n minus 1 plus the now extra stall cycles that are needed to provide for the branch instruction into obviously each cycle time, TP. So k is actually 5, right? K is 5. N is, anyways, 5 will be ignored. N is very, very large. 10 to the power minus 9, so 10 to the power 9, so it will be anyways ignored, but still. So I will not write this right now. I will keep it n as it is, because here also it is in terms of n only. So this is 0.4 n into TP is 1 nanoseconds. So like I can ignore this, right? I can ignore this 5, 4. This will be anyways ignored, because it is 1.4 into 10 raised to power 9 into 1 into 10 raised to power minus 9 seconds. So this will come out to be 1.4 seconds simply. So your answer will be 1.4 seconds. This is a simple question, and these are simple questions you will be able to solve after solving this question. This was the highest difficulty level that they can ask. Okay, this is the highest difficulty level that they can ask. Previous question was also a very good question. Okay, so I hope you're enjoying the lecture. So obviously, what are the solutions to this branch hazards or control hazards? Basically, we use delayed branch, right? We have the software solution. Basically, compiler detects it is a branch instruction, so we introduce stall cycles that we have already been doing, that we have already learned, right? So our next instruction will be fetched only after this branch is evaluated. So we have our compiler does this. That's why it is known as a software solution. Compiler gives a delayed instruction, also known as dummy instruction, which is not related currently. It is some other instruction. If the compiler needs to evaluate this, compiler, it doesn't want to sit idle. So let's say you are on a factory, okay, and you are building manufacturing cars, right? And your previous stage has stopped due to some delay or some hazard, okay? So now what you will do? Will you sit idle? You can do some other task. Your manager will tell you, okay, currently project A is installed, you do project B. So I will do project B, which is completely independent of project A. So it can happen. Or sometimes what they do is they provide no operations. We don't do anything. We just sit idle. Just like stalls. Same as stalls. Nothing else. Same as stalls. Understand, we are not doing anything. We're just sitting idle here. Okay, we're not doing anything. Sitting idle. So we introduce stall cycles, and only after this execution of the branch instruction, then only I start my instruction fetch. I go to the target instruction and I fetch my target instruction fetch. Okay, so like this I have explained previously as well. Only after the execution of, only after the evaluation of branch instruction, I will evaluate I will fetch next instruction, also known as target instruction. Okay, so like this we already know. I have just written this thing here. So another way to do is branch prediction. Although like this is very difficult, but I have told you, right, if I know already beforehand that 50% will be 50% time I will take the branch, then I have like shown you the example that execution time gets reduced. So we can do this. We can implement this hardware solution. If the driver anticipates the direction, like I'm giving you an analogy beforehand with experience, right? With experience, the driver knows whether I need to take the, like you are inside your like a very busy road, right, and there is a left turn and right turn, and if the driver is situated in that location for years, right, he knows at 8 p.m. whether I need to take the left turn or right turn. By experience, he knows the congestion or the jam will be on the right turn, so he will not take the right turn, he will take the left turn. Okay, by experience. So I just given you an analogy, but actually there are many algorithms and those things go inside the computer. We don't want to get into that, but if we are able to predict the branch, right, then we can save the time. Okay, if I'm not taking the branch, then obviously it will be sequential, so we are saving the time there. Okay, so if the guess is correct, no delay, because I fetch the next instruction instantaneously. If wrong, the driver backtracks or flush the pipeline. So if our guess was wrong, right, so we have fetched the sequential instructions, but those are of no use because I will go to the target instruction, so I have to flush everything. I have to delete everything, right? That is the main thing. So if the pipeline prediction is correct, pipeline proceeds without any interruption. If the prediction goes wrong, pipeline rolls back the branch instruction, rolls back to the branch instruction. It goes back to the branch instruction and deletes whatever that pipeline has done till that point. Okay, it will delete all the other things and then it will fetch the correct target instruction. Okay, so now we'll study about the structural hazards. So what are structural hazards basically? So let's understand with a basic example. Imagine a busy grocery store with only one cash counter. Two customers arrive at the same time but can't check out simultaneously because the counter is already in use. There is a line, right? There is a cash counter here. Okay, and two people are coming to the cash counter, right? But I have only one cash counter, so this can only service one cash counter because someone has to pay. Then like he will give the bill to the person, right? He will take the his purchase items. So I can only resolve one customer at a time. But if two customers come, I cannot do that. So first I have to resolve this customer, then the next customer. So I've also given an example of like movie and friend. Okay, so then what we do, we create a queue. Basically, we create stall cycles. We tell this person to wait until I finish with this person, with this customer. Then after finishing, this customer goes away and then this customer comes in. So what we do, we just provide a stall cycle. So let's understand with a computer example, right? This structural hazard also is known as resource conflict because two instructions are actually at the same cycle are actually applying for the same resource. Occurs when two instructions require the same hardware resource at the same time. Consider a pipeline with one memory unit shared for register fetch and data access. So I have only a single memory unit, right? Where I have told you, right? So data comes into the memory unit from any location, okay, and then again data goes out of this memory unit to any memory location. So I have only a single memory unit. So if I have a single memory unit, what will happen? Instruction one is load R1000. So basically what it does is load the whatever content that is stored in memory location 1000 and load it to R1. Instruction 2 is store 2000 R2. So basically whatever is present in R2, I will store that value in memory location 2000. So assumption is we access the memory in the operand fetch stage. Okay. So what we can understand is that here I am doing instruction fetch, correct? So this is also accessing the memory, right? Because we have only a single bus, so instruction is getting fetched from the memory location that is address is pointed by the PC, so it gets fetched here. Then I am decoding, fine, and in this decode I am also doing instruction fetch. So I can do the instruction fetch here, okay, because there is no resource conflict here. Okay, here I am doing a operand fetch after this. Okay, so if I am doing a operand fetch, this should be decode. Actually, this should be decode the instruction. Okay, So what we can assume is one assumption what we can take. This is a bit wrong. My assumption is operand fetch, right? Operand fetch takes 2 cycles. So here it is a standard 5-stage pipeline only, but one of the assumption is operand fetch takes 2 cycles. Okay, it takes 2 cycles. So if operand fetch takes 2 cycles, then a third cycle I will do operand fetch, and in the next cycle as well I will do operand fetch. Everything will be shifted by a single cycle. So this cycle will also be a operand fetch because I need 2 cycles, and this cycle will be execution phase, and this cycle will be write back finally. Okay. So now here first instruction it is totally fine, so all the cycles are fine. In the next instruction, in second cycle I am doing instruction fetch because I know first cycle I do instruction fetch of instruction I1, and in the second cycle I do instruction fetch of instruction I2. Next I can decode the instruction, no worries. So this will be decode only, this will not change. This will be decode the instruction. Next is where the things will change actually. Here I am supposed to do the operand fetch, but currently I can observe that operand fetch is getting used. So what does operand fetch do? It fetches the operand from the memory location to its own general purpose register. Correct? But memory unit, I have only a single memory unit, right? I only have a shared single memory unit. If I have a single memory unit, so memory unit is already getting used to execute this particular micro operation, right? So I cannot use operand fetch here. Same example as cache register. Already a memory unit is getting used. I cannot use that same memory unit here. So this will cause a stall cycle here. Stall. I have to provide a stall cycle here. Then after I provide a stall cycle, this instruction I1 is not using the operand fetch anymore. It's not using the memory. It is using the ALU. So now I can use the operand fetch here. Now I can use the operand fetch without any resource conflict, because here in this particular cycle, fourth cycle, they were asking for the same resource at the same time, but I cannot do 2 things at a single time. I can only do 1 thing at a time. So after this operand fetch will happen, no worries, and after that this will take 2 cycles of operand fetch. So this will be operand fetch and this will be execution. Okay, and this will be write back. But here is the main concept that is underlying concept, right? We are having resource conflict. Okay, so here actually this should be in cycle 4. In cycle 4, both instructions try to access the memory, causing 1 stall cycle, because I cannot give access to both the instructions. So what I will do, first I will finish this, because I am in the middle of this. I will finish this, then I will come to this next instruction, right? Solution in real life: add more cache counters, so we can add more memory units. If I add more memory units, so I can handle multiple customers simultaneously. So in pipelines, what we do in real life, we do add more cache counters. In pipeline, we add separate memory units for instructions, fetch and data access. So we can do all these things. We can add separate units, right? But sometimes it is not possible, so we have to only provide stall cycles. Okay, so this is a comparison table between all the different types of hazards. So what is structural hazard? It is like the hazard that we studied now. It is a resource conflict, where if I have multiple instructions competing for the same hardware resource. Data hazard: an instruction depends on the result of the previous instruction still in pipeline. So remember, only raw dependency are the true. Raw, what is raw? Raw agent or something like that, right? So raw dependency is the true dependency. Other dependencies are basically false or anti-dependency. What was the anti-dependency? Anti-dependency was WAR. You can write a short notes like this, right? This is anti-dependency and this is true dependency. And what was false dependency? False dependency was W, because we're just writing back. Okay, it doesn't matter. So this was the false dependency. Okay. And in control hazard, we have just studied, that is branch or jump instruction disrupt the sequential flow of the instruction. Okay, hence we have to provide stall. So everything The solution is mainly providing stall cycles. Okay, now we will solve few questions on this particular hazards. Okay, for a pipeline CPU with a single ALU, consider the following situations. The J plus ith instruction uses the result of jth instruction as an operand. So let's say J is 3. So fourth instruction, okay, uses the third instruction. So result of third instruction is getting used in the fourth instruction. So I can do it like I have just taken an example that R1 equals to R2 plus R3, and I do R4 equals to R5 plus R6. Okay, the execution of a conditional jump. Okay, like these are following situations that it telling me the execution of a conditional jump instruction. So this is a branch type instruction, right? Branch control hazard can happen. The jth and j plus ith instruction require the ALU at the same time. This is basically resource conflict, right? Resource conflict. This is like a structural hazard. And this is data dependency. What are they telling? Which of the following can cause hazard? All of them can cause hazard. Like these are the 3 different types of hazards. So all of them obviously can cause hazards. So option D will be correct. So let's solve the next question. So in the next question, we have a code and it is run on a pipeline processor, and I have a extra branch delay slot. Like this were old questions, that's why the language is not clear. I will explain. I have an extra branch delay slot here. Okay, and what they're telling me, which of the instructions can actually occupy the delay slot? Where should I place the delay slot to properly for this code to function without any modification? So if I place a delay slot here, right? If you tell me I will place the delay slot here, I2, will that be beneficial for me or not? Okay, now here, right, what I'm doing is, if I observe this R2, right, is getting used, like it first I'm writing, then I'm getting reading from it. So actually there is a raw dependency between I1 and I3. So obviously I cannot just simply add a branch delay slot because there is a raw dependency. So this instruction has to wait until this instruction gets evaluated. So I cannot modify anything between I3 and I1. In I2 and I4, if I see, I again have a raw dependency, right? This R4 is getting used here, right? And there is is there any raw dependency? Yes, there is a raw dependency because this R4 will read the value of R4, right? So there is a raw dependency here as well, and there is a raw dependency here as well. Read after write, right? All these are raw dependency. So I cannot mess up with I2 as well. I3 as well I cannot mess up. So in I4, actually I will give the delay slot Y. Why I will give the delay slot in I4? Because I can give the delay slot in this, between this instruction, right? I can give it here. What I want to do is, even if this instruction gets delayed, right, it doesn't affect the previous instruction. Okay, even if this instruction gets delayed, it won't affect the previous instruction. Okay, it won't basically. So that's why I can place a delay here, because what I'm doing, I'm branching to a label if R1 equal to 0. So it's not like these two instructions are related. R1, I'm not changing anything. I'm not changing R1. I'm just reading R1 here, right? So I can provide a delay here because I don't have any data dependency. So instructions I4 can be used to provide a delay slot. Now I know this question is confusing. If this is confusing, skip this question, because these types of questions will not be asked nowadays, because previously what used to happen was language was not clear. That's why the question, understanding the question is very difficult. Now they will explain the question very well, because you get a paragraphs of question, right? So it's very big question, so don't worry, you'll understand it. So now let's come to few new terminologies like pipeline efficiency. What is pipeline efficiency? Pipeline efficiency is a measure of how effectively the pipeline is being utilized. Okay, how effectively I am able to utilize the pipeline. It is expressed as a ratio of achieved speed up to the ideal speed up, typically represented as a percentage. In an ideal pipeline with no hazard, the pipeline operates at 100% efficiency, because my install equals to 0, right? Install is 0. Now if install is 0, then if n is very large, right? If n is very large, this should be installs, not st. This is installs. What is this basically? This is S ideal. S ideal will be the highest, because it talks about the highest speed up that can be ever achieved. So S ideal, S achieved will be this. Now if install is 0, right, and my n is tending to infinity, what will happen? This will be Tn by Tp, which is equals to S ideal. Then my efficiency is 100%. That's why it is written 100% if the install is 0. Okay. If install is 0, n is very high, this nn gets cancelled, it is Tn by Tp, S achieved is equals to S ideal, that hence my efficiency is 100%. Okay. So that is the, this should be installs, right? That is basically the definition of efficiency, pipeline efficiency. So sometimes if they will ask questions from pipeline efficiency, if they are asking questions from pipeline efficiency, you will understand that they are talking about the ratio of S ideal upon S achieved. Remember, S ideal, sorry, not, I'm telling you the wrong thing. It will be S achieved upon the S ideal as written here, right? Because obviously S achieved will be lower than the ideal, the maximum speed up that I can achieve, right? It will be always lower than that. So there is a question, this came on ISRO, I think. So a pipeline P operating at 400 megahertz has a speed up factor of 6. So its speed up factor is 6 if it is operating at 400 megahertz, right? So S achieved is 6 if my F clock is 0.4 gigahertz. Okay, so and I am operating at 70% efficiency. So my efficiency of the pipeline is 70%. From here, can I find out the ideal speed up? What will be S ideal? I know S ideal, S achieved upon S ideal is equals to efficiency, right? So S achieved is 6 upon S ideal equals to 0.7 basically. So S ideal will be what? Will be 6 by 0.7. 6 by 0.7. So it will be 8.571. Now this is equals to what? This is S ideal is equals to Tn upon Tp if n is very high, right? Now they have not mentioned anything. And what do I want to know? I want to know the number of stages. Okay, they have not mentioned the number of stages, and I want to know the number of stages. They have not mentioned whether the stages are balanced or not. So what I will do is I will assume nothing is mentioned. So I will assume all stages are balanced. Okay, so if I assume all stages to be balanced, then my Tn will be what? Tn will be simply KTP. How this comes? Lecture 1 of pipelining. I have explained how this comes, right? So Tn by Tp will be K. So this will be equals to K. Now obviously K is an integer. It is the number of stages. So if it is number of stages, right, K has to be greater than equals to this number. Why it has to be greater than equals to this number? Because only in the balance case Tn is equals to KTP. For all other cases, if system, I will assume if system is unbalanced, right, if pipeline is unbalanced, my Tn will be less than equals to KTP. Why? If you remember, I shown you example as well. Let's take example of 4 stage, 2, 2, 2 and 2 nanoseconds, right? So in case of balance, my Tn will be simply equals to 8 nanoseconds, basically sum, and which is equals to 4 times 2, which is 8, right? If I add and then multiply 4 times 2, that is same. But in this case, if it is unbalanced, right, 1, 2, 3, 4, then what will be my Tn? Tn is sum, right? Sum of all the stage delays. Remember, Tn is the non-pipeline execution time for a single instruction. So it will be 1 plus 2 plus 3 plus 4, that is 8, 10 nanoseconds. But what will be KTP? KTP will not change, right? KTP will be what? KTP will be the maximum. Maximum is 4 nanoseconds. So it will be 4 times 4, that is 16 nanoseconds. So it will always be, KTP will always be greater than Tn. Okay. So I will just use this. I will not equate this directly with equals to Kate. I will just use this particular thing, right? So from here, what I can say? I can say that my K will always be greater than or equals to Tn over Tp. This will always be the case for balance, unbalance, all cases, right? And what is my Tn over Tp? Tn over Tp is here, right? Tn over Tp is 8.571. So K has to be greater than equals to 8.571, and K is an integer. We know number of stages, it can be a fractional number, it has to be integer. So from the options I can see only one option is telling me that K will be greater than 8.571. So obviously option D will be correct. All other options are rejected, right? K has to be greater than 8.571. All these options are saying otherwise. Okay. So I hope you have understood this conceptually. Okay, because many students, many students and educators also, they just mug you up this concept that this will be always true. This is not always true. Okay, if it is not balanced, unbalanced, it will not be always true. So you have to identify the relationship. What is the exact relationship? Okay, so now let's solve the next question. So we have a pipeline processor with the following 4 stages: instruction fetch, instruction decode, and operand fetch, execute, write back. So we have 4 stages, and in this only operand fetch happens. Okay, fine. The IF, ID, WB take 1 clock cycle each to complete the operation. So I will write the things down. Okay, I will write the things down. So IF, now this is a very, very good question. IF, ID and WB take 1 clock cycle, and my execution stage depends on the instruction. How many cycles the execution stage will take, it actually depends on the instruction. The add and the sub instruction need 1 clock cycle. So in execution, if I have add and subtract, it will be 1 clock cycle, right? If I have add or subtract, it will be 1 clock cycle. Okay. And the multiplication instruction needs 3 clock cycle. Multiplication actually needs 3 clock cycle. Okay. Next, operand forwarding is used in pipeline processor. When can you use operand forwarding? If they are telling me operand forwarding is used, that means they are only talking about ALU to ALU operation. ALU to ALU operation. Else I will not be able to use operand forwarding. Okay. Only if I use ALU to ALU operation, then only I will be able to use operand forwarding. What is the number of clock cycles taken to complete the following sequence of instructions? So first I have add, then I have multiplication, then I have subtraction. Okay, how many clock cycles will I require? So first, what I notice is all these, right, are general purpose registers. All these are GRPs. So basically, I can use the concept of operand forwarding. operand forwarding, because all of them are ALU to ALU operation. Okay, so now let's break it down. Let's solve it step by step to understand this better. Then I will tell you a method 2. Okay, first I will solve it using table method 1, which is the lengthy one. So this is instruction I1, right? And I1, everything is same. Everything will take one clock. Okay, everything will take only one clock cycle only, but except the multiplication, right? It is a addition instruction, so it will take one clock cycle. So it has 4 stages. So first I will do instruction fetch. Then I will decode the instruction and fetch the operands, and then I will execute. It will take only one clock cycle because it is an addition operation, and then I will write back the result. So it has no issues. Okay. Then in the second clock cycle, I will start the instruction fetch of I2. Then I will do instruction decode. As soon as I decoded the instruction, I got to know that it is a multiplication type instruction. So how many execution cycles will it take me? 3 execution cycles. So it will take me 3 execution cycles. 1, 2, 3. After that, I will write back the result. Why 3? Because it is a multiplication type instruction. Okay. Then in the instruction 3, I again fetch the instruction. That is fine. I fetch the instruction in the cycle 3. That is fine. Then I decode the instruction, right? ID. Then I got to know it is a subtraction type instruction. And then I will do the execution here, because it is a subtraction type instruction, and you will be totally wrong. Why? I told you, right? There is a control hazard here. I cannot do execution, because for execution I need ALU, right? To perform subtraction I need ALU, and already it is being occupied by the previous instruction. Okay, ALU is already occupied. Okay, it is already occupied in the previous instruction. So I cannot use execution here. I have to provide a stall. Here also I have to provide a stall. Then after this, finally my execution phase is over for the previous instruction. Finally I can do execution, right, of the third instruction. So execution will start here. It will only take one phase, one cycle, because it is a subtraction type instruction. Then I will write back the result. So how many clock cycles it took me? It took me total of 8 clock cycles to finally execute, right? If I didn't have provided the stall, I would have finished earlier as well. But I had to, because the ALU was already occupied. So that's why I had to provide only provide a stall cycle, provide 2 stall cycles. Okay, I had to provide 2 stall cycles. So this is the method 1 to solve. Number of cycles will be 8. Option B will be correct. So 8 cycles. Now what is the other method? Method 2. First of all, I want to say only valid when a single type of hazard is occurring. Okay, only valid for a single type of hazard. For multiple types of hazard, I cannot use this. I simply cannot use this. Okay, so what I can say is that assume, or we know this, assume assume each take one cycle to execute a instruction in the pipeline, right? Because like after, if n is very larger than k, we take only one cycle to execute a new instruction. So assume each instruction take one cycle to execute the instruction. Correct? Or like but we already, okay, one thing I know, no need to assume in this one. What we know, to execute without hazard, to execute n instructions without hazard, number of clock cycles. What was the number of clock cycles to execute n instructions without hazard? It was k plus n minus 1. Now without hazard is this, right? But I have structural hazard. So how many stall cycles I have to give for a single structural hazard, right? So if I have a structural hazard, this is same like branch time instruction, right? So I have to give stall cycles. How many stall cycles I will give? So I have to wait till the resource is freed. So when will the resource be free? I can observe as soon as I finish the execution, right? For all this, we don't have any hazard. For addition, subtraction, it takes 1 second only. So we don't have any problem. But for multiplication, I have to give extra 2 stall cycles. Why? Because my execution finishes on which stage? 1, 2, 3, 4, 5. Fifth stage. My execution finishes on the 5th stage. After this only I can start execution of the next instruction, right? So for multiplication, okay, for multiplication, how many extra cycles I am taking? Extra cycles. How many extra cycles I am taking? Anyway, execution anyway for all the instructions, it already takes 1 cycle only. For addition, it takes 1 cycle. For subtraction, it takes 1 cycle. That has been accounted here. That has already been accounted here. But how many addition cycles does the multiplication instruction take? How many addition? 2. So extra cycles 2. Multiplication takes 2 extra cycles. So what will be my total number of cycles? Total number of cycles to execute the program. It will be without hazard, whatever I get, and extra cycles due to hazard. So obviously every time you won't be able to draw the table on those things. This is how you calculate. Without hazard I calculate, it is k plus n minus 1. So k is what? K is, it is a 4-stage pipeline. N is how, what? I have 3 instructions minus 1. So it will be 6 cycles. And extra cycles for multiplication, I have to provide 2 extra cycles for multiplication. As I have only 1 multiplication instruction, if I had 2 multiplication instructions, I have to multiply it by 2. So it will be 6 plus 2 into 1. This 1 is due to what? As I had only a single multiplication instruction. So this will be simply 8 cycles. I got back the same answer that I solved in the previous, using the previous method, but you will not be able to use it always. This you will be able to use it only for a single type of hazard. Okay, so that is the important thing that I wanted to take away. This method is applicable if I have single types of hazard. Previously also we are doing the same thing, only we are adding the extra cycles, but it was stall cycles because we are waiting for the branch condition evaluation. Okay. So let's solve the next question. So here, right, another interesting thing, operand forwarding was present, right? So if operand forwarding was present here, right, if you observe that this R2, I was like, I ignored this, I was doing what? This is a RAR type dependency, right? If I see read after write type dependency, and this is also a read after write type dependency. So as soon as I finish my execution here, I instantly give this value of R2 is given to the second instruction, right? Second instruction as soon as I finish, as there is a operand forwarding. Okay, and here as well, the R4, as soon as I execute this R4, right, at the next stage only I start my execution, because I directly give the R4 into the next instruction. Okay, I don't take it from here, right? I don't take it from here. I directly from this execution stage I give it to the next instruction. Okay, that's why operand forwarding was present. Now, if operand forwarding is not present, how will you do? That is the question, right? If in the same question, provision of operand forwarding, if in the same question provision of operand forwarding is not present, then how many clock cycles we would require to execute the same instructions? How many clock cycles would it require for us to execute the same number of instructions? Okay, so here operand forwarding is not there, so we don't have any shortcuts. We have only this method only. We cannot use any shortcuts. So actually I have to bring more space into this. So what we can do, right, so you can take a bit top. So this will be increased, this will be increased, this will be increased. Let me put this as T10, T11 and T12. Okay, so if operand forwarding is not present, what will happen is that here I will start with my instruction fetch of the instruction I1, then I will decode and do the operand fetch, then I will execute. As it is an addition operation, I will only take one cycle, then I will write back the result. In the next instruction I will do the instruction fetch from second cycle. I cannot instantly do instruction decode and operand fetch. I cannot do it. Why I cannot do it? Because I am still waiting, right? I am still waiting for it to provide me the result. Okay, actually it was ID. Yeah, ID is here. Previously what was happening was here, right? He was actually, yeah, previously what was happening is like, yeah, I can do ID here. That is fine, I can do ID here, but I cannot simply start my execution from here. Why? Because right now this connection is not there, operand forwarding is not present, right? So I cannot simply take the operands from the previous execution stage to current execution stage. I cannot simply do that. Okay, operand forwarding is not present, so this is not possible. So I cannot do execution. What I have to do, I have to provide stall cycles. I have to wait for this to be finished and this write back to happen, right? So I have to provide stall cycle here, and after this write back has happened, then only I will start my execution. Okay, then only I will start my execution and my instruction decode as well, because this will also be not correct. Previously there was operand forwarding, that's why my execution phase was directly getting its operands from the previous execution instruction. Okay, but now I don't have operand forwarding, so I will take the operands from the instruction decode stage only, and I cannot do instruction decode here because this instruction hasn't been done yet. So again I have to provide a extra stall cycle here as well. Okay. So finally after write back, now I am ready. Now I can start. Now I can do ID. Instruction decode. Then I can simply do execution. I know it is a multiplication type instruction, so it will take 3 clock cycles. And then finally after this I can write back the result. Now here, right, after this I can do the instruction fetch here. I can do the instruction fetch in the 3rd clock cycle. But can I do ID? No, right? Because if you remember correctly, that your 3rd instruction, right, was dependent on the 2nd instruction. It has a raw dependency. So I cannot directly start the operand fetch here. I have to wait till the write back because there is no operand forwarding. So I have to provide stalls until here, right? So all this will be simply stalls. This will be stalls, right? And after the stalls only I can start my instruction decode. This will be ID. Then I will have my execution of addition, not addition, this is subtraction. And then finally I will write back the result. So after the 12th cycle, finally my instruction will be over. So how many cycles it took me? It took me 12 clock cycles. So this will be 12 clock cycles. Now you will say, sir, does this have any shortcuts? No, actually. This doesn't have any shortcuts, right? This doesn't have any shortcuts. You have to solve it like this only. If no operand forwarding is present, you have to solve using the tables. Okay, so that is very difficult. So let's solve this next question. Okay, so we have a 5-stage pipelined processor, and it has instruction fetch, instruction decode, operand fetch, perform operation, write operands. Okay, so 5 stages are there. Okay, so K is 5. And what it is telling, the perform operation stage takes 1 clock cycle. Sorry, the IF, ID, OF, WO take 1 clock cycle. So I have IF, ID, OF, WB are 1 clock cycle. Okay. And the PO of add a subtraction take 1 clock cycle. So PO, perform operation of add / subtract take 1 clock cycle, and the perform operation and the perform operation for multiplication instruction takes 3 clock cycles. For multiplication it takes 3 clock cycle, and for division it takes 6 clock cycle. Okay, so operand forwarding is used in the pipeline. So operand forwarding is used only for ALU to ALU operation. I can observe that everything is register. So it will, everything is ALU to ALU operation, right? Because we are using general purpose registers. What is the number of clock cycles needed to execute the following instructions? So will I draw the table again? No, I won't draw the table again. Okay, so we'll simply calculate. So without any hazard, because there is some hazard. What is the hazard? If I observe, if I just copy this thing, okay, and paste this here. Here, what can happen is there is a data dependency, right? Where is the data dependency? Here I have a data dependency, right? R2 and R2. I am writing, this is a raw type data dependency, and again here there is a data dependency. Now I have to check whether I have enough gap between instruction I0 and I2 so that there is no data dependency. If this instruction takes enough time, I have to actually check that. Okay. So how can I say is that, and okay, anyways, okay, no, this also has data dependency, right? So I don't have to check anything. This right here also I am reading back from R5 after updating it, and okay, so it's totally fine. Yeah, everything has a data dependency. This also has a data dependency, right? So like everything has a RA data dependency. So how will I solve it? Simple. Without hazard, how many cycles it would take me? It will take me k plus n minus 1, which is equals to what? Is equals to k. It is a 5-stage pipeline. N, I have total 4 instructions. 4 minus 1. Okay. With hazard extra, how many extra I am requiring, right? Due to the data hazard, how many extra stall cycles I needed to provide. Okay, how many extra? This is 3, right? I have a multiplication instruction here. This is 3 clock cycle, and there is a data dependency. Just hold on. And not R2. Sure. Actually, there is no data dependency here. There is no raw data dependency here. From here to here, there is no data dependency, but there is what? There is hazard, right? There is control hazard actually. Control hazard. Not control, sorry. There is structural hazard. And this, there is a data dependency, but that I can ignore because here also there is a structural hazard. And why I can directly use? Because they have told me operand forwarding is used. So as operand forwarding is used, I can ignore raw or data hazards. Why? Because of operand forwarding. So I will only consider structural hazards because operand forwarding is present. I will not consider data hazards. Okay. Previously, also I ignored that. So how many extra cycles do I need to give for structural hazard? For multiplication, how many extra cycles it takes, including excluding the one cycle that anyways every instruction, every micro operation takes. It takes 2 extra. So this will be 2 extra. Multiplication and division will be 5 extra. So how many multiplication instruction I have? 1. How many division instruction I have? 1. So this will be extra cycles will be 2 into 1 multiplication plus 5 into 1. So this is 1 multiplication and this is 1 division. So total number of cycles will be what? 9, and this is 8 plus this is 2 plus 7, right? 2 plus 5, 7. This is 15. So total I will be requiring 15 cycles. So option B will be correct. Now you might say, sir, you ignored the data hazard. Yes, I ignored. Because why did I ignore the data hazard? Because the stall cycles provided due to structural hazards is more than enough to deal with the data hazards. I don't need to provide any extra stall cycles. Homework, you can make the table and see, observe yourself that I don't need to give any extra stall cycles for data hazard. Okay, because operand forwarding is there, data hazard won't be occurring. Okay, I hope you have understood this point. Let's solve this next question. So this question I took, I think, in the starting of lecture as well, but this question is a bit different. What we have to do? We have to say that what we have to find out. A pipeline processor uses 4 stages, and this like we have to evaluate, and everything is register to register. Everything is ALU to ALU, ALU to ALU. Okay, and they are telling me that the IF, ID, WB stage take 1 clock cycle each. So IF, ID and WB, it is a 4 stage, right? They take 1 clock cycle. and the other stage, execute stage, it depends on the instruction. Execute stage take 1 clock cycle for add, subtract and store. So EX takes for add, subtract and store, it takes only 1 clock cycle. Okay, for 3 clock cycles for multiplication and division operations. 3 clock cycles for multiplication and division operations. So it is 3 clock cycles. So how many extra I required? How many extra? Extra here for add is 0 only. For multiplication division I have to provide 2 extra clock cycles. Okay. Now what are they asking us? They are asking me operand forwarding is used in the execution stage to ID stage. Okay, operand forwarding, like operand is forwarded directly from the execution to the next ID stage, right? Directly it is forwarded. So I don't need to provide extra stall cycles. Okay, I don't need to provide extra stall cycles here. The number of clock cycles required to complete the sequence of instructions. So same question again, how many clock cycles I will require? So again, I will find without hazard how many clock cycles I require. Without hazard, it is k plus n minus 1. Correct? K plus n minus 1. That is, it is a 4-stage pipeline. How many instructions I have? Total 1, 2, 3, 4, 5. 5 instructions I have, minus 1, and extra. How many extra cycles I needed to provide, right? So for add, subtract, store, I don't need to provide, but I have a multiplication, I have a division. So I have 2 instructions which take 2 extra cycles each. So this will be 2 times 2. So total number of cycles will be 8 plus 4, that is 12 cycles. Okay, so answer will be option B. I can show you using the diagram as well. Okay, so like this will be a bit lengthy. So what I can do, right? I can do one thing. First of all, I can delete this and I can take from here. So I have drawn exactly the table, instruction cycle table for you guys to exactly explain what is actually happening. Okay, although I have done the computation, but I wanted to show you how it is happening. Here first instruction is an addition type instruction, and I can observe there is always a dependency. This is a dependency, this is a dependency, this is a dependency again, and this is again a dependency, right? So tell me in the comments below what is this dependency, question number, and tell me in the comments below what is this type of dependency. Okay, so we have a data dependency, right? And what is the type of the data dependency, you can tell me in the comments below. So but that data dependency will not be affecting us. So data dependency stalls will not be present due to data dependency. Okay, stalls will not be present due to data dependency. So what will be present basically? What will be the fault basically? So why will stalls be not present? I will explain in this table. I will explain. So first instruction is an addition type instruction. So it will have instruction fetch, it will have instruction decode and operand fetch, then execution, and then write back. Simple as. So I will start from next instruction. Next instruction is actually a multiplication type instruction, right? So I will just write in brackets what is the type of each instruction. This is add, this is multiplication, this is subtraction, this is division, and this is store. Okay, so what I can observe is I am doing the instruction fetch, I'm doing the instruction decode and operand fetch. I can instantly start the execution of multiplication. Why? Although there is a data dependency here, but as there is operand forwarding, what will happen? The execution stage operands will go directly into the next instruction execution phase, because I have operand forwarding element. If operand forwarding was not enabled, I had to provide a stall cycle here, and my instruction decode and operand fetch would have started from here, right? But it is not. Operand forwarding is present, that's why there is no hazard due to data dependency. So we will see the hazard will come only due to structural dependency or resource conflict. Okay, so I know execution phase for multiplication will take 3 cycles and then write back will happen. Now for the next instruction, the instruction fetch will happen in cycle 3. The instruction decode and operand fetch also will happen in cycle 4. But the problem is I cannot exactly start here execution phase. Why? Because the previous instruction is actually using the ALU. It is using for to compute the multiplication, right? I cannot start execution phase here as well. Simultaneously in the same clock cycle, 2 execution phase cannot work. I have a single person for a single stage, right? A single person cannot do 2 tasks at a time. So I have to provide a stall cycle. These stall cycles are provided due to what? These stall cycles are provided due to structural hazards. Stall cycles due to structural hazards. Okay, these are not due to data dependency. So here I have 2 extra stall cycles. So how did it came here, right? Already I have shown you using the method what we do, but here we can visually see actually where the 2 extra stall cycles are present. Again, what will happen then after this stall cycles, my execution will start for the subtraction instruction, then write back will happen. Again, instruction fetch can happen after this, right? At the 4th clock cycle, instruction decode can also happen. But also you can observe that the execution after the execution of this multiplication, I am directly feeding this result into the execution of the next instruction, right? Because there is a data dependency between multiplication and subtraction. If you observe, R6 is being read back here in the sub instruction, right? After being writing. So obviously I can directly forward this here, right? If let's say operand forwarding was not there, I had to wait till this write back. So I had to provide a stall here, then execution, or then the instruction decode would have happened, right? So I had to provide extra stall cycle. So that is the issue that I had to face. Okay, so I hope you understood this point. So yeah, again same thing will happen here as well, and same thing will happen here as well. You can visualize and see. I will not explain this further, but I hope you are understanding the point. The point being that if I have operand forwarding and like there are some structure, like the hazard will be done due to only either structural hazard or branch. Okay, there it won't be due to 2 things if operand forwarding is present, and this method is only valid for a single type of hazard, right? If I have 2 types of hazard, then I have to do visually. That's why I have explained 2 methods, visually and both like just writing, right? Method, like writing method, shortcut method. Okay, so I hope you understood this point. Let's solve the next question. An instruction pipeline consists of 4 stages: fetch, decode, field, execute, and write, result write. The 5 instructions in a certain instruction sequence need these stages for different number of clock cycles. So now actually different instructions has different number of clock cycles in different number of stages. Okay, so things are more and more difficult. So I have seen many educators teach you, like you have to visualize, you don't have any method, but I will tell you one single method with the help of which you will be able to solve these type of questions, right? So they are asking me find the number of clock cycles needed to perform the 5 instructions. Different stages has different number of clock cycles. How will I solve this question? Now first of all, you have to actually draw the table here as well. If you don't draw the table, you won't be able to solve it. So this, right, this can be solved with a shortcut as well. If the cycles are given, this can be used with a shortcut. So the thing is, you have to draw these type of table, like exactly same table, but everything will be empty. everything will be empty. Okay, so this much hard work you have to do, and this will not take you much time. This table will not take you much time to draw than this table, right? Drawing this table is very difficult, but this table will not take you much time. Okay, you have drawn the table, you have written the stages, and you have written the instructions. Now what you'll do, you will write the addition. So you will write the, like, what does this box represent? This box represents the current clock cycle. Okay, so let's assume I have started with the instruction I1, I have fetched the instruction I1, right? So this is the current clock cycle. Then I went on to the decode. So after what clock cycle this decode instruction will be over? After third clock cycle, right? Because first clock cycle has gone for instruction fetch, then I have to take another 2 clock cycles for decode to happen, second and third. First clock cycle instruction fetch, second and third for decode. Then how many clock cycles will I require to execute? Only 1 clock cycle, right? So I am at third clock cycle currently. I will require 1 extra clock cycle to execute. So it will be 4, the current clock cycle. So after this is done, how many clock cycles will I require to write back? I will require 1 clock cycle to write back. So currently I am at 4. So current clock cycle number will be 5. So after 5 clock cycles, my first input will be ready. I1 will be processed, basically, will come out of the pipeline. Now, what about here? When I will start my instruction fetch. So I will start my instruction fetch after, like, before it was 0 clock cycle, I took 1 clock cycle, right? Now I am at first clock cycle. I need 1 extra clock cycle to do the instruction fetch of I2, right? So I will be at, current clock cycle number will be 2. After this instruction fetch has happened, current clock cycle number will be 2. Now comes the interesting point. Here, how many clock cycles will I require to decode instruction I2? They have told me it will require me 2 clock cycles to decode the instruction I2. Now, this represents what? This represents the current clock cycle number. It is telling me that the instruction I1 decode will finish after 3 clock cycles. So from this 2 observations, right? These 2 observations, what I can deduce from these 2 observations, that decode of I1 will finish after third clock cycle. And what this particular thing is telling me, this is the first point that I can deduce. Second point is what? Second point is IF, that is instruction fetch of I2 will finish after second clock cycle. Now tell me one thing. Can I instantly start my decode of instruction I2 from third clock cycle onwards? No, I cannot, because after the third clock cycle only the decode stage is getting freed, right? This stage is getting freed only after the third clock cycle due to instruction I1. So I cannot start my decode from second clock cycle onwards. So from this I can deduce I have to start my decode from fourth clock cycle onwards. I cannot start from third clock cycle onwards because third clock cycle is busy. Already that stage is busy. Due to what? Due to which hazard? Due to structural hazard. Or what do we call it? We call it resource conflict. Okay. So in short, what we do is, here what will be written? Here actually what thing will be written? That is the most important point. If I have some other color, yes, this is the other color. What will be written here is, like I can tell you, logically what should be written is, mathematically what should be written is maximum of top and left plus its own clock cycles plus how many cycles it takes. Own, this is my own language, own cycles. What do I mean by maximum of this? So whichever one will be maximum, right? From that cycle onwards, I will start, because I cannot start from second clock cycle, because it is telling me that the decode stage is being used now. Okay, decode stage is being used until third clock cycle. I cannot start. Let's say if this was 4, I cannot also start from 3 as well now, because the instruction fetch hasn't happened, right? The previous stage hasn't even finished and I am decoding the current instruction, which is not possible. What I am telling, let's say if this is 4, let's assume that this is 4. Now you tell me, if this is 4, then this first line will be, then the second line will be instruction fetch of I2 will finish after 4th clock cycle, right? Okay, after 4th clock cycle. And decode of instruction I1 will finish after 3rd clock cycle. You will say that decode stage is free now, so I can do my decode after 3rd clock cycle. No. The instruction fetch of I2 hasn't even been completed. How can I decode? Instruction haven't been fetched yet. How can you decode the instruction? Instruction itself hasn't been fetched yet. How can you decode the instruction? You cannot decode the instruction, right? So you have to wait. You have to put a stall cycle again. Okay. So obviously I will choose the maximum of these two. I will always choose a maximum of these two. If the instruction hasn't been fetched yet, how can I decode the instruction? If the current stage is busy, there is resource conflict, how can I use the decode stage? I have to give stall cycles. So that's why I told here maximum of top plus left plus my own number of cycles. So what will be this value equals to? Maximum of top plus maximum of top and left is what? Maximum is 3. 3 plus its own number of clock cycles that it takes to complete that particular stage is 2. So 3 plus 2, this will be, I will write this better. This will be, just hold on. This will be 3 plus 2. Okay. So this will be 5 actually. Can write this. Three plus 2 will be 5. Okay. Now in the next stage also I will do the same thing only. I will not explain again. I have already explained. If you couldn't understand this, please go and rewind. I will apply the same procedure here. I will check for the maximum of left and maximum of top. Like I will check from the maximum of left and top. So what is the maximum of left and top? It is 5, right? After 5 clock cycles, this I2 decode stage is getting finished. Although my execution stage is free from the previous instruction, but I cannot use it because the decode stage hasn't finished yet. So I will wait for 5 clock cycles, then I will add with my own clock cycle delay. What is it? 5 plus 2, that will be 7, right? So this will be 5 plus 2, it will be equals to 7. Now this also will be same only. So next ones I will write directly. So this again I will choose the maximum. What is the maximum? Maximum is 7, and what is its own delay? 1. So it will be 8. So here again, left I don't have anything, top I have 2. So what is the maximum of left and top? It is 2 only, and its own delay, that is 2. So it will be 2 plus 2, so that is 4. Then again the same thing, maximum of left and top, it is 5 plus its own delay. 5 plus 1 is, sorry, not 5, yeah, 5 plus 1 is simply 6, correct? This will be 6. Okay, then the maximum of these two, that is maximum is 7. 7 plus its own delay. 7 plus its own delay is 3. 10. Then again I will check the maximum. Maximum is this 10. 10 plus its own delay is 2. 12. Again I will check the maximum of top and left. Left I don't have anything. Top I have 4. So 4 plus its own delay 1, that is 5. same thing, maximum 6 plus its own delay, that is 9, maximum plus its own delay, that is 12, maximum, both are same only, so it will be 12 plus its own delay, that is 13, again maximum, that is 5 plus its own delay, that is 6, maximum 9 plus its own delay, that is 11, maximum 12 plus its own delay, 13, and 15 finally. Okay, so after 15 clock cycles, I will be able to perform my 5 instructions. My 5 instructions will be processed. Okay, so this question is very elegant. If you couldn't understand, please rewind that portion again. That is the most understanding point of this particular question. So this type of question can also be asked. This topic is for different type of branch delays, right? If I have different types of, not branch delays, if I have different types of delays of each stage, then how will I solve? This is for the case of what? Actually, this comes under the topic of non-synchronized pipeline. Okay, I haven't explained this, but actually what happens is this comes under the topic of non-synchronized pipeline, right? Because every stage is not taking the same amount of delay, and you can observe that what a hassle this is to compute the total number of clock cycles that the execution will instructions will take, right? What a hassle. That's why we don't use non-synchronous pipeline. So this is also the same type of question only. I have 4 instructions and each of them take different type number of cycles, so in each stage. So what will be the number of cycles needed to execute the following loop for I equals to 1 to 2. So 4 stage pipeline instruction. Okay, the number of clock cycles required by the 4 instructions is given. S1, S2 are stages S1. What is the number of clock cycles needed to execute the following loop for I equals to 1 to 2? So for I equals to 1 to 2, basically I have a loop here for I equals to 0, I equals to I'm starting from I equals to 1, I less than equals to 2, I plus, right? So there is some code. This I1 instruction is there, then this I2 instruction is there, then this I3 instruction is there, then this I4 instruction is there. This is running, and after that what we do, we simply execute. So they are telling me how much time it will take me to execute this particular loop. So how many times the loop is running? So here I observe the loop is only running once, right? Loop is only running once. Okay, or yeah, loop is only running once, because I am starting from I equals to 1, then I reach the second stage. Okay, it should go from for I equals to 1 to 2, for I equals to 1 to, okay, this is not actually less than equals to, this should be less than 2. Okay, the loop is only running only once. Loop is running only once. It is only running once. It is not running more than that. If it would have run number of times, I will tell you how to solve. Okay, so if it is running only once, I can calculate for once how much time this whole cycle, right, it will take. I1, I2, I3, I4. So again I will do for the first I will simply write back the values. This will be 2, then I will add 2 plus 1, that is 3, then I will add 1 again, this will be 4, this will be 5, then again I will use the formula. Maximum of top and left, maximum of top and left is 2 plus its own delay, that is 1, so it will be 2 plus 1, 3. Again maximum is 3 plus its own delay 6, maximum plus its own delay 8, maximum plus its own delay 10. Okay, then again, okay, everything is correct here, right? This 2, yeah, this is correct only. Then maximum plus its own delay, that is 5. Okay, this is only, I have only 4 instructions, right? Okay, this anyways can be gone. Maximum plus its own delay, that is 7, maximum plus its own delay, that is 9, maximum plus its own delay, that is 13, maximum plus its own delay, that is 6, maximum plus its own delay 9, maximum plus its own delay, that is, yeah, that is that is what, that is actually this will be 11, maximum plus its own delay, that will be 15. Okay, so one thing is wrong. Actually this should be I less than equals to 2 only. I made a mistake. It is going from I equals to 2 to 1. How many times it will run? Actually, my mistake. It will not run twice. It will run, loop is running twice. Why? Like at the start only I was right, but at the end I got it wrong. So why it will run twice? So it will start from 1. So for once it will execute. Then for I equals to 2 again it will execute. Right? Again it will execute. So if it executes again, it will be just twice. Right? For once the loop is taking 15 cycles. So for once one loop 15 cycles, 2 loops, it will be 15 times 2, 30 cycles. So your option D will be correct. So it will take total of 30 cycles because the loop is running twice. Why? Because if you know a bit of C coding, you will know that if the loop is something like this, for I equals to 1 to I less than equals to 2, then for I equals to 1 it runs, then again I increment my I, it goes to 2, then again I check the condition. For I less than equals to 2, 2 is equals to 2, the condition is 2, so I will run the loop once again and then it will end. Or if you want to know, I told you a shortcut, right? If you ever want to understand how many numbers are there between two numbers between a range, you can simply do what? You can simply apply this formula. Max minus min plus 1. So 2 minus 1 plus 1. So it is 2 times. So that's why the loop will run twice. Okay. So I hope you understood this point. So let's do this last question. Okay. Let's do this last question. So what is this question? We have a instruction pipeline of a RISC processor has the following stages. I have ID, operand fetch, perform operation and write back. 5 stage I have. Okay. The IF, ID, OF, W all take 1 clock cycle. So except the perform operation, right? Everything takes 1 clock cycle only. 1 clock cycle. Okay. For every instruction. Consider a sequence of 100 instructions. In perform operation, 40 instructions take 3 clock cycles. So in perform operation, I have take 3 clock cycle. Okay. Then I have 35 instructions. That take 2 clock cycle. And I have remaining 25 instructions which only take 1 clock cycle. Okay, so assume that there are no data hazards, no control hazards. There is no data hazard, no control hazard. What kind of hazard can happen? Only structural hazard. The number of clock cycles required for the completion of execution of the sequence of instructions. So how many clock cycles it will require me? So again I can use that formula, right? Simple. It will be what? It will be without hazard. How many clock cycles I will require for 100 instructions? K plus n minus 1. I have 5 stage, 5 plus 100 minus 1 and extra stall cycles I have to provide. Why? Due to structural hazard, right? Because obviously this takes more time. So obviously this instruction will use the perform operation stage more number of times. So the next instruction cannot use that. So how many extra cycles it has? Extra cycles. This will be 3 minus 1 extra cycles. Anyways, 1 cycle we anyways allowed to everything. This will be 2 minus 1, and this will be 1 minus 1, that is 0 extra cycle. So how many total number of extra cycles? Okay, so this will be this plus, for 40 of this instruction I take 3 minus 1 extra cycle, right? So 40, each instruction takes 3 minus 1 extra cycles. How many of these instructions I have? 40. That's why this is 40 plus again 35 instructions take 2 minus 1 extra cycles. So total extra cycles will be 35 times 2 minus 1 plus 25 instructions take 1 minus 1, that is no extra cycle. That's why a 0 is there. So why am I writing this? Because like I think you will find this pointless. Why am I writing this? But there is a point to it. To understand this conceptually why these terms are coming. That's why I am writing this. Okay. So total number of cycles will be 104 plus this will be 80 plus 35. Correct? 80 plus 35. So this will be 115. So 115. So 219 clock cycles. So total number of clock cycles that I will need to finish this instruction will be 219. Okay. Please do keep in mind that this method is only valid for when only one hazard occurs throughout the pipeline, else this will be not valid. So this is a very important point, key point that I wanted to tell you at the end of today's lecture and at the end of our YouTube journey. So I hope you have enjoyed. Like we have covered most things on pipelining. Few things will be left that will be covered later on. Okay, you can check in the comments for more information about regarding that. Okay, so few things are left for pipeline. Most things GATE syllabus is covered for EC domain and for placements as well. Most things are covered. Few things are left that will be, you can get the information from the comments below. Okay, so I hope you have enjoyed. If you did, please go in the comments below, tell your review, how you liked, what you hated. Okay, what you liked, what you hated, all those things you can tell. Please do. Don't forget to press the like button. Don't forget to subscribe to my channel for more content, okay, related to digital VLSI and analog VLSI. I hope you have enjoyed this journey of COA, and I hope I have kept you engaged and you have developed an interest in the subject if you already didn't had any interest in the subject previously. So yeah, that's it about our journey of COA on YouTube. Thank you for watching, and I will see you in the next video. Until then, happy learning.